Welcome back, everyone. Think of today's session as your university masterclass on reliability measurement. So far in our software engineering journey, we've talked a whole lot about how to actually build reliable systems. But today, we're shifting gears. We're going to learn how to scientifically prove our reliability targets are met rather than just blindly hunting around for bugs. We're going to look really closely at how we gather hard, undeniable data on failures over time. Okay, let's take a quick look at our roadmap for today. We're going to build our foundational knowledge sequentially, starting with an introduction to reliability measurement, defining the operational profile, outlining the statistical testing process, and exploring the hurdles we face. Then we'll wrap up the whole thing with a comprehensive review of Chapter 11 to make sure you are absolutely ready for your exams. Let's start with the big picture. Why do we actually need to measure reliability in software engineering? Well, we already know how to specify our quantitative reliability targets, right? We know about POFOD, the probability of failure on demand, and ROCOF, the rate of occurrence of failures. We can write those metrics into a requirements document all day long. But here is the absolutely crucial question. How do we actually prove we hit them? How do we verify that the system we've just spent months building has actually achieved that required level of reliability? To do this, we use something called statistical testing. Now, I want to clear up a really common misconception right out of the gate. Statistical testing is a process explicitly geared toward measuring reliability. It is not about finding and fixing faults. Finding bugs and fixing them is a totally separate process called debugging. Statistical testing is purely about running the software, observing it, and gathering mathematical data to compute an observed reliability metric. Before we can even begin this statistical testing, though, we really need to understand the core mechanism that drives it. Before we run a single test, we need to define an operational profile. So what exactly is this? An operational profile is essentially a mathematical model of real-world user behavior. It identifies the exact classes of inputs and the precise probability that users will trigger them. For instance, if you are replacing an existing telephone switching system, telecom companies have vast databases of historical call patterns. They know exactly how the system is used on a daily basis, so they can map out the probabilities of every single type of input perfectly. This distribution illustrates the profile brilliantly. Notice how the absolute most probable inputs, the things users do every single day, cluster tightly to a small number of classes over on the left. Meanwhile, the highly improbable uncommon inputs trail off in this incredibly long tail over to the right. When we test our system, our test data has to match this exact probability distribution to be valid. So, just to briefly recap this vital concept, we simply cannot measure real-world reliability without first building a statistically accurate blueprint of how the system will actually be used. The operational profile is that exact blueprint. Let's move into the methodology now and see how this blueprint builds into the actual testing process. There are 4 chronological stages to statistical testing that you need to know. First, you study existing systems of the same type to define your operational profile. Second, you generate a massive dataset of test data that mathematically matches that exact profile, which usually requires an automated test data generator. Third, you run the system using this data, meticulously logging every single failure and exactly when it happens. And finally, after observing a statistically significant number of failures, you compute the observed reliability to see if you've hit your POFOD or ROCOF targets. While this mathematical approach is conceptually beautiful and sounds perfect on paper, bringing this theory into reality involves some pretty significant hurdles. There are 4 principal difficulties we face in the real world. First, operational profile uncertainty. Honestly, your model of user behavior might just be wrong. Second, the immense cost of generating massive data sets. If you can't automate it, manual data generation is prohibitively expensive. Third, statistical uncertainty. If your system is already highly reliable, very few failures occur, meaning you have to run tests for an impossibly long time just to get statistically significant data. And fourth, the sheer difficulty of recognizing failures. If your system specifications are written in ambiguous, vague, natural language, observers might actually disagree on whether a failure has even occurred. Furthermore, what's really fascinating here is the innovation problem. Think about it. If a system is highly innovative and totally unprecedented, there is zero historical usage database. Users might interact with it in wild ways the developers never even anticipated. In these edge cases, it is practically impossible to predict how users will behave, making the operational profile little more than a wild guess. And if your profile is a guess, well, your reliability measurements will be entirely untrustworthy. All right, let's shift gears now into a macro recap of the entire reliability engineering chapter to really consolidate your knowledge. First up, do not fall for the classic exam trap of confusing these three terms. According to Rendell's model, a human mistake, like a programmer's typo, causes a system fault, which is a literal defect in the code. When that faulty code executes, it leads to a system error, which is an erroneous internal state. Finally, this results in a system failure, where the service is visibly not delivered to the user. For example, a programmer mistakenly adds 1 hour to a clock without checking for midnight. That's the fault. At midnight, the clock reads 2400 hours instead of 0300 hours. That's the error. Because the time is invalid, the system crashes and fails to send a scheduled weather report. That, my friends, is the failure. You absolutely must also remember our critical quantitative metrics. POFOD is used for systems with intermittent demands, like a chemical reactor's emergency protection system. ROCOF is for regular, continuous demands over time, like a bank processing thousands of transactions an hour. And finally, availability is simply the probability of the system being operational and up and running at any given time. When faults do inevitably occur, because they always do, we rely on fault-tolerant architectures based on redundancy and diversity to keep the system running. Protection systems are independent backup systems that monitor the main system and safely take over if it fails, kind of like the backup computers on the space shuttle. Self-monitoring architectures use separate computing channels and compare the outputs. If they differ, a fault is detected immediately. And N-version programming is where entirely different teams write different versions of the software from the exact same specification, running them in parallel and voting on the correct output to ensure one team's blind spot doesn't crash the entire system. Finally, remember the golden rules for dependable programming. You should always minimize faults by actively including redundancy and stringent input checks in your program. Guidelines like checking array bounds to prevent buffer overflows or setting up strict execution timeouts are your very first line of defense against catastrophic system failures. To conclude our masterclass today, let's look at exactly what you need to focus on for your exams. For your upcoming tests, I want you to ensure you can accurately list the 4 stages of statistical testing, from studying the profile all the way to computing the metric. You must be able to precisely define an operational profile as a mathematical model of input classes and their probabilities. And finally, you need to confidently summarize the core fault tolerance strategies we've discussed, specifically the diverse architectures used to catch and handle errors at runtime. Congratulations on mastering reliability engineering. It really is a vital skill for building the critical infrastructure of our future. But as we wrap up Chapter 11, it leaves us with one incredibly provocative question that's going to carry us straight into our next lecture. If a system is completely, mathematically reliable, does that actually guarantee it is safe? We're going to explore exactly why the answer is a resounding no when we tackle Chapter 12, Safety Engineering. I'll see you then.